the relationship between the volume and pressure of a gas. We got that title down? Excellent. And you don't have to draw this or write this. Don't write anything. This is just showing what you obtained, all right? So you saw graphically that the pressure is inversely proportional to the volume of the gas. Which, the variable in which I change doesn't matter. If I change one of the variables, the other variable automatically changes with that inverse relationship. So I always have to have a fixed amount of gas. I always have to have trapped gas. And it always has to be at a constant temperature in order for this to be true. As soon as you start varying those other things, there's other things that come into play. But that is always the case. In our experiment, as I make the volume smaller, the pressure goes up. There's our inverse relationship, right? And I can move the V to this side, and then I'm going to have P times V is equal to some constant, K. We called it K yesterday, all right? That means the pressure times the volume in an isolated gas is always constant. So if the pressure goes up, the volume has to go down so that P times V always remains the same. All right? So that's what they mean by the constant. We can put that, let's not worry about that. We can put that together in Boyles Law formula, which you've already written down. Hopefully that's on your lab somewhere. Some of you might have put the V's first, but it doesn't matter. Typically, we write it simply as P1V1 equals P2V. Now, just like in our concentration dilution equation, again, the units don't matter. Does anybody remember what was the most important thing about the units? Somebody have a hand up there? No? What's the most important thing about the units when we use that dilution equation? Didn't matter what units we used, but they had to be the same because they had to cancel out. So in this equation, because it's a ratio, pressure could be in kilopascals, but pressure could also be in atmospheres. Doesn't matter. They could be in torr. They could be in PSI, etc. They can be any pressure unit. Same with the volume. We're not locked into any volume units here. They can be liters, they can be milliliters, they could be meters cubed, again, etc. The main thing is that the units must be the same. Be the same. Okay? So now at this point, we'll do some example problems. I'll give you a little practice sheet. I'll let you work for a little bit, and then we'll work on the next two variables, volume and temperature. Those are the next ones we want to look at. Okay. Yep, don't mind that. You can write that question down. As I stated, this is just like the problems that we have dealt with concentration. It doesn't matter which one you designate as 1 or as 2, as long as they're together. So you can go ahead and solve this one without me. I don't even really need to wait. I've got a balloon. It's got a volume of 22.4 liters at 273 Kelvin and 1 atmosphere. What will the new volume be if the pressure is doubled to 2 atmospheres and the temperature remains constant? So the temperature data, I don't even need. It's constant. I'm looking at the relationship between this volume and this pressure. I'm now changing the pressure. I want to know what the new volume is. So again, as long as they're together, I'm looking at the data. I've got a P1. Sorry, I should have started with V. There's the V1. V1, 22.4 liters. And the pressure that goes with that is 1 atmosphere. I want to know what the new volume is. V2, question mark. And the second pressure, P2, is 2 atmospheres. Now we should be able to think this through actually quite logically. I'm doubling the pressure. I'm making the pressure 2 times as big. If the relationship is simply an inverse, what's the new volume have to be? Yep, half of the half of the old volume. Because if you double one variable, then because of the inverse relationship, double inverse is 1 over 2. It should be half the volume. And that's another way to think of inverse relationships. They really are that straightforward. If I triple the pressure, what happens to the volume? What's it going to be? If I triple the pressure, what would the volume become? What's the inverse of triple? 1/3, right? If I made the pressure become 1/2, what if I made the pressure get smaller by 1/2 of its value? What would happen to the volume? It would be doubled because it's an inverse relationship, all right? So keep that in mind. That's always a quick check. Sometimes, though, I don't give you nice questions where it's not exactly doubled or exactly, it might be like 2.735 or something like that, so you got to do some math. But keep that in mind. It's an inverse relationship. Okay, so P1 V1 equals P2 V2. Put your numbers in. 1.00 atmospheres. V1 22.4 liters. Hopefully some of you are ahead of me. You shouldn't have to be waiting for me to fill this in. P2 is 2.00 atmospheres, and V2 is what we're looking for. We're dividing off the 2. Oh, the horizontal line stinks. You know that. 2.00 atmospheres is being divided off. There we go. 2.00 atmospheres divided off. That is gone. That is gone. 22.4 divided by 2. What is that? 11.2 liters. V2. All right. So that illustrates a couple of things, how we use the equation, and the fact that you can use some logical sense on this stuff as well if you've got some easy, numbers to work with. We doubled the pressure, we have half the volume. And let's do one more. I think one more. Yep. No need to write down that homework. Actually, I'll just take it off the slide because the homework is on the sheet. Even the textbook questions are written on that sheet that I gave you. Great word there that you're coming across right now. Isothermally. What a great word. Isothermic. We've encountered iso in this course. Hopefully I've impressed on you what it means. So if we have the volume change under isothermal conditions, it means the volume has changed, but the temperature has stayed the same. And we need that to be the case, because when we study our variables, Boyles law is true when temperature is constant and the number of moles is constant, then we can see that relationship. Hopefully you're way out ahead of me doing the calculations. I've got, I'm going from 10 to 30, and the initial pressure was. So 10 and my pressure go together. V1 is 10 liters, and that goes along with the initial pressure, 1140 millimeters of mercury. V2 is 30 liters, and I want to know what P2 is. Again, I'm going quickly because I'm hoping you're out in front of me here. P1 V1 equals P2 V2. Whoops, that's a horrendous V. 1140 millimeters mercury. Volume 1.0 liters. P2 is what we want. 30 liters. Divide off the 30 liters. Divide off the 30 liters. Notice the units, sorry, I didn't want to get rid of the 10. The unit liters cancel. That's why the units have to be the same. The 30s also cancel on that side. P2, what do we got? Yep. 380 milligrams. 80? 80. 380 millimeters mercury.